Hey all, is my audio properly coming? Am I audible? Someone could please write in the chat box if I'm audible or not, then I can continue. Could anyone please write? Okay, yeah, so I'm audible. So welcome to this event by deeplearning.ai and Developer Students Club, Netaji Subhash Engineering College. So this is the introductory event where we introduce you to. Okay, I'm audible probably. Okay, so this is the introductory event where I introduce you to the basics of machine learning and neural networks, especially. But before anything, let's hear a welcome note by Dr. Andrew Ng. He is the founder of deeplearning.ai, and after that, we'll come back soon. So.
AI and build your career. I hope that being part of this community will help you to do so. To give you a proper welcome, I'd like to show you around the Deep Learning.ai offices and meet some of the teams so that you can see where it all happens. Oh, hi, Edgar. Do you want to tell our friends at Pine AI what you do at Deep Learning.ai?
Sure. Hi, everyone. I make articles and other media that help people learn about AI and help them understand the huge impact that AI is having in the world. Today, I'm putting together the next issue of The Batch, our weekly newsletter, and I'm looking for the biggest stories of the week to keep our readers informed.
What's been the most surprising thing you've run into working on The Batch?
How much is going on in this field? There is never a dull moment. You might think from the outside that machine learning engineers really understand everything about AI, but nobody understands everything about AI because this field is just coming to life right before my eyes as I put this thing together every week.
All right, I know you're really busy, so I should get back to it.
Thanks. See you later.
Let's go meet Jian, who helped me create the deep learning specialization. He's working on an exciting new project. Hey Jian, so do you want to tell the people at Pine AI what you're working on?
Yes, sure. I'm leading a project for Volterra, focusing on helping people get offers in AI and navigating their career by testing their skills, preparing for interviews and certifying them, as well as matching and referring them to good jobs in AI.
That's really cool. And what's the most exciting part of your day?
You know, the AI field is new, organizations and jobs are still misunderstood. So I'm excited to help people understand what different types of jobs exist in the field, what tasks they will work on, and what skills are needed to achieve those tasks.
That's really important work. Well, it's nice chatting, and now let's go chat with Oracle, who is on the product team. Do you want to say hi to our friends at Pine AI and let them know what you're working on?
I would love to. Hi, everyone. I lead the product team in deeplearning.ai, where we create AI education content accessible to people all around the world. People like you.
And what are you most excited about right now?
I am so excited to see our community grow and to see how eager people are to learn more about AI.
Thanks, also. So, as you can see, our team is working hard to support you and help you learn. It's never been easier than before to break into AI. So if you want to build a career, you can leverage online resources available, including open source code, data sets, papers, and online courses like the deep learning specialization on Coursera. As part of this journey, I hope you get your hands dirty too. Don't be afraid of diving in to build your own project. Or go ahead and try to replicate a research paper that you're excited about. one thing that I've seen a lot of people succeed is if you can build a community or find a community of fellow deep learners you can meet with and study with on a regular basis. In fact, I hope that this Pine AI meetup that you're at right now will be a good place for you to meet these people. I hope you enjoyed the event today and that you learn a lot both from the talks and from each other. And once again, welcome to the deeplearning.ai community.
Okay. So I hope are you having some issue? Okay, am I audible properly now? Okay, yeah, I'm audible. Okay, fine. So I hope you enjoyed the video. It was a welcome note by Dr. Andy Ng. And so let's begin our session today. I'll be sharing my screen and we'll go through our presentation. There's a Q&A session at the end of this video. So if you have any doubts, please keep them noted and I'll make sure to answer them at the end of this video. Right. So, and also please be sure to check your emails after this event, since we'll be sending feedback emails, filling which you'll be getting 50% discount on any deeplearning.ai courses from Coursera. So without further ado, let's share my screen. Fine. Let's change this layout first. Okay. Fine. So for the last few months, you might have heard a lot about AI. You have heard them being applied by different industries. Several startups are applying AI and developing products that are amazingly doing good in the market. So before diving into the coding part, let's have a look at some of the popular applications of neural networks, right? So you might have seen self-driving cars applying neural networks and artificial intelligence in them. So a popular example of which is Tesla. You all know Elon Musk from Tesla, and then AI is also being applied in entertainment industry, facial recognition, virtual assistant. There's a very popular virtual assistant startup from India as well. I remember Haptic.ai. Then there's the Google Assistant that uses AI for answering your questions. There's fraud detection, natural language processing, news aggregation, and fraud news detection. The government of India and several other governments from across the globe are using AI in the time of COVID-19 to fight fake news, right? So AI is also used in detecting developmental delays in children, that is for medical purposes, colorization of black and white images. Uh, I hope some of you might have seen the recent trending video of a popular black and white movie by Satyajit Ray, known as Pathir Panchali, uh, that being converted to color form using artificial intelligence. It's on YouTube. It's a very fun video. You can watch it after the event. And there's also adding sound to silent movies. Then there's healthcare. AI is being used in healthcare industries for detecting uh, lungs diseases, for detecting COVID-19, also for brain MRIs. So different application in medical field as well as it's used in automatic machine translation, automatic handwriting generation. There's some very popular repositories in GitHub as well where handwriting generation is used. I was going through some of them the previous day, and demographic and election predictions. Of course, we all know Donald Trump heavily used artificial intelligence in his election process, right? So, but moving apart from all this hype and all these applications, we really talk about machine learning a lot. But what actually are neural networks and how do you implement them? So once you go beyond the hype of neural networks and start coding for those neural networks, start actually writing the code in Python, then how does it look like? Just a minute. I have some difficulty in my audio. I guess my audio is back. Okay, sorry for the interruption. Yeah. So how does the code look like, right? So this is a popular picture that you might have seen across the internet. This is the comparison between traditional programming and machine learning. So what do we do in traditional programming? We take data and we write the program or rules, right? Uh, to achieve a certain task, we write the rules and then give the data, and the traditional programming gives some output. However, in machine learning, we don't give the rules. We let the computer figure out the rules by itself. We just give some previously collected data and uh, the output for those data. And then we let the machine learning model write the rules, right? Uh, so, but this isn't really machine learning totally. This is just a training phase. Because what would we do with a program or set of rules? That would be probably the model file, that .h5 file, right? However, we want output to be generated also. So next comes the inference phase. So in the inference phase, we provide new data, unseen data to the thus trained machine learning model, and then get some new predictions. So let's jump to the actual structure of a deep learning code. I learned deep learning especially from the deeplearning.ai specializations, especially the ones by Lawrence Moroney. He is a developer advocate at TensorFlow. So there's a very lovely specialization by him, TensorFlow in practice. So I learned from there. And so let's jump to the actual structure. So I divide a machine learning code into 5 important segments or distinct parts, right? So first, we need to import the packages that we'll be using. I especially use TensorFlow. You are free to use PyTorch or other packages as well. Then we accept the data input, the previous data that we have in collection, and then we define the model. Then fit the model to the data and then make predictions. Let's jump to these steps properly and have a closer look. So I'll be taking an example from a very popular machine learning code that's readily available by Google. You can find this code all around in Google. introductory textbooks. So this is all we need for writing a machine learning code. So in this code, we are trying to figure out the output of a linear function, right? So this function, if there are data points 1, -1, 0, 1, 2, 3, 4 in x, and in y there's -2, 1, 4, 7, 10, 13. So these are really the x versus y data uh, that is supplied to the model. And then we want to provide new data and see the output. So in neural network, basically we are trying to figure out a function. We supply the x value, and then we want the function to predict the y value, right? So let's get to the breakdown of this code. First, I will be skipping the part 1 and 2. Part 1 is just importing the packages. As I told you, I will be using TensorFlow. Import TensorFlow as TF. As TF, we're just uh, writing TensorFlow in short form for ease of use. We won't be writing TensorFlow all the time, we'll be writing TF. And NumPy. NumPy is a package that helps us represent our data as list, right? And Keras is a Keras basically helps us to uh, represent data in sequential layers. You see tf.keras.sequential. So we can define a neural network as a set of sequential layers using Keras, right? So let's jump to it and then we'll see what this specifically means. Okay, let's jump straight to the model. You have seen this line, tf.keras.sequential keras.layers.dense units equals to 1, input shape equals to 1. So what's this? This is one layer of a neural network model, right? This is just one layer. First, we'll be starting with one layer and then we'll jump to more layers later on in the video. But this is just one layer of a neural network model, and this is the simplest layer. So I'll be explaining what does this sequential mean in the latter part of this video. However, this is one layer and this units equals 1. This is one neuron. We'll be working just with one neuron to start with, and this input shape equals 1. So this is, we are taking one value only. We are taking one value from x and predicting the value for y, right? So since we are just taking one value, so input shape is 1. In case we had, suppose y equals to mx plus nz, if suppose this was the function, then there the known variables would have been x and z, and we are predicting for y. So in that case, input shape would have been 2. So this, and then we compile the model. While compiling the model, we use two functions called optimizer and the loss function. So I told you what a neural network does is basically figure out the function that correctly represents the input data and the output data, right? So how do we do this? This Before jumping to a demo of this thing, I'll explain this to you deeply later. Before jumping to that, let me say what's an optimizer is. So an optimizer makes a guess, a random guess, and then the loss function calculates the difference between that guess and the actual value, right? Suppose the function is y equals to 2x. Suppose the function is y equals 2x. So for value of x, say 3, y equals to 2x, the value of x is 3. And the value of y will of course be 6. So suppose the value predicted was say 5. So there's a difference between the actual value and the value that's predicted, right? That in this case 6 minus 5, 1. So that's the loss. And the optimizer will try to make a random guess, and then the loss function will calculate the difference between the actual and the predicted, and then the optimizer will try to reduce that loss and make another guess. So this is basically what a neural network does. So, and then in the next part we did model.fit and print. So in the model.fit, you see we used x's, y's, epochs equals to 500. What's an epoch? Epoch is the number of times we repeat the previous process, this process. Optimizer and loss means the optimizer predicts a random value, the loss is calculated, and then the optimizer predicts another value to reduce the loss. So how many times do you repeat this cycle? So that's known as an epoch. So here we tell to repeat that for 500 times, right? And then print model.predict 10. So here we are trying to predict the value for the new x for which we want to the y value to be predicted, right? So this is the 10. Suppose in the y equals to 2x example I gave, if I want to find the value, what will be the value of y if x equals to 10? So in that case, x will be 10 and the output will be, you might expect that will be 20. However, it won't be 20 because machine learning deals with probabilities. You won't exactly be getting 20, it will be very close to 20, probably 19.9999 or 20.00001, but maybe not 20, because in machine learning we deal with probabilities. So, okay, you see, we start with, when you start with the first epoch, the machine learning model just makes random guesses, and they can be equally wrong and equally right. So with as we proceed through the epochs, the accuracy increases, right? So you saw we use this to optimizers as SGD. What's this SGD? And what's mean squared error? SGD is stochastic gradient descent, and I'll be explaining that to you. It's a very popularly used optimizer, and the loss we used was mean squared error. However, for different scenarios, you might be using different types of loss and optimizers. So some of the commonly used loss functions were, uh, if we are dealing with a classification problem, suppose we need to classify it's an apple or a orange, right? So in such classification problems, uh, we use commonly cross entropy loss, or also known as negative log likelihood or log loss. These are different names of the same thing. So this is one popularly used loss function. Also, we use hinge loss or multi-class SVM loss. And for regression loss, regression is tasks like the one I said before. Suppose y equals to 2x. So this is a straight line, right? Or the data moves continuously. As x increases continuously, y2 increases continuously. So we're not classifying here. We're uh, just trying to find a point in the function, right? So there we use mean squared error, or also known as quadratic loss or L2 loss. And we also use mean absolute error, or the L1 loss. We also use Howard loss, smooth mean absolute error. I'll be linking a detailed slide to when to use all this loss and what this does in the document that will be linked in the description box. Please check it out after this session. But let me explain two of the popular loss functions. Here we used mean square error, right? So what mean square error does, if you are a student of statistics, or if you had statistics in high school, you might know this error. This is a very popularly used error in high school as well, mean squared error. So mean squared error takes the difference between the prediction and the ground truth, square it, and average it out across the whole data set, right? Suppose on the prediction, as I told you, uh, was in y equals to 2x. Suppose x was 3. So the actual value of y should have been 6. However, uh, suppose the machine learning model predicted the value was 5, right? So 6 minus 5, that's 1 squared. And then we repeat this for, suppose there were 5 or 10 data points like this. So we repeat it for those and divide it by the number of data points, right? Also, this the log loss that we use popularly for regression tasks. You can have a walk through this in the slide. It will be linked in the description box. Uh, do you have much time? Okay, no. We need to finish. This is there. You can go through it, the log loss, and understand when to use this log loss actually. Let's jump to commonly used optimizers. So these are the most commonly used optimizers. There's ADA Delta, ADA Grad, ADAM, ADAMAX, FTRL, NADAM, RMS Prop, SGD. So among these, the underlined optimizers, these are the most commonly used ones. ADA Grad, ADAM, RMS Prop, and SGD, right? So I've explained some of these optimizers as well. So I'll be explaining stochastic gradient descent, or SGD, here for now. However, you're free to walk through the slide. Because of time constraint, I won't be able to explain you all these three. But however, since we use SGD, I'll be explaining it to you. So suppose, okay, let me walk through a demo and then describe it to you, right? It will be much simpler. Okay, so uh, you can visit this link, and this is a very nice demo of this gradient thing that I just mentioned. So there will be able to learn. Just a minute, I will show you a demo of it. Let me open it. Okay, I hope my screen is visible. The demo that I'm showing, I guess the screen is visible, right? Could you please confirm if my screen is visible, the demo that I'm showing? Okay, it's visible, right? So these are, suppose we take, suppose 12 random points. These are the 12 random points, right? We can generate random points by clicking here. And so we see in machine learning, we are trying to draw a function that properly takes into account all these points and reduces the loss, right? As I told, the loss function is reduced by the optimizer. So you see, here's the loss that's calculated, mean squared loss that I was describing. So see, in y equals to mx plus c, if I change the m, the loss is increasing and decreasing. And we can decrease it more by changing the b and m values. So this is the best plot. See, the mean squared error is really less. So this is the best plot line to these data points. So now if I change the m, you'll see the loss will increase. Also, if I change this m to this side, the loss will increase. Right. Now let's get back to the video. So, in stochastic gradient descent, we take a subset of, I guess this is not full screen. Yeah, in stochastic gradient descent, we take a subset of this. We take a subset of all the data points and uh, then calculate the gradient descent for it. So a gradient descent is, let's say, if you have a curve, right? If you have a curve and you want to find out the minima of that curve, how will you proceed? Suppose, let me share with you my paint screen, and then it will be easier for you to understand. Suppose you have a curve like this. So this is the x-axis and this is the y-axis. Suppose you are at this point. How do you know we are approaching the minima? The minima is this point maybe. So how do you know you are approaching this minima? If for that we calculate the gradient descent. So you saw the loss was decreasing and then it again increased, right? So this is, consider this the loss. You saw the loss was decreasing and then it was again increasing. So consider this as the loss. So for knowing if we are proceeding towards this minima, we calculate it using gradient descent. So let's jump to the this again. Next we have, please walk through this different types of optimizers after this event is over. Uh, so, but we used only one single layer, right? Uh, However, in most cases, you won't be using one single layer. That's really inefficient, and we'll be using stacks of layers, right? So, how to do that? Let's dive deep into a deep learning code. Okay, that was fake. Okay, so here you see we have used three layers in this model. Suppose we take a image in this case and then uh, predict what image it is, right? Suppose we take the fashion MNIST data set. It has images of clothes, shirts, pants, shoes, uh, and all such things. Suppose we take a shirt. Uh, we need to predict if the image is of shirt or not. So for that, we are using three layers. Now, as I previously said, in the first layer we take input shape. In the previous time, it was input shape equals 1, right? But why? Because we are calculating for one value of x, the value of y equals to mx, suppose. So x was only the variable. Here, all the images are 28 by 28 pixels, right? So for that, we take input shape equals to 28, comma 28. So this is the input shape, 28 by 28 pixels images. And then we use something called flatten. So what is a flatten? You see, do you have it? Yeah, we have it in the latter part. I'll explain all these things to you also. Let me say, but in flatten, so remember earlier where our images were square. The image that I said in this data set are 28 by 28 pixels square images, right? So flatten takes that squares and turn them into a one-dimensional array, one-dimensional set, because machines are efficient in processing one-dimensional arrays much more than those images, right? So flatten just reduces this dimension from 2D to one-dimensional array, right? Uh, we use the sequential layer for stacking up of layers. You see, we stacked up three layers on top of each other. So for that, we use the sequential part. And then after this flatten function, we use a function called dense. What is dense? Uh, okay, in the next slide, I will explain you why we write this dense. And in the last layer, we have 10. So this 10 is in the fashion MNIST dataset. Actually, there are 10 classes, right? Shirt, pant, shoes. So like this, there are 10 classes. And if I am if I'm to predict the image of a shirt, it's just one out of those 10 classes, right? So we have to predict from a set of 10 classes. So this is the 10. The output would be 1 out of 10. So this is the 10. And I'll come to this layer in the next slide. You might be wondering what's a ReLU and softmax. Okay, I'll make you understand this in the next slide as well. So yeah, so this is a diagrammatic representation of what we did in the previous slide. You see, first we take flatten out the 28 into 28 into one-dimensional array. So this is the input layer and it's flattened in one-dimensional array, as you can see. And this second layer, this is known as the hidden layer. Here are those 128. Those 128 are the neurons, or you can say functions. There are 128 functions. and we'll try to fit all this uh, pixel data into those functions, and then predict the output, get the output from these functions, right? uh, if you had taken statistics in college or high school, you would know a theorem which states that uh, any polynomial can be expressed as a product of uh, several functions, right? So see, it will take all this pixel data as input in this function, and then try mapping those, try tuning the parameters of those functions, and then map to the output that we provided, in this case shirt. So it will do that for all these neurons or functions, f0 to f127, and then predict in this output layer. And why then dense? We call it dense because you see, we are taking all these pixel values and mapping it to each of these functions, right? This 128, each of in each of these 128 functions, we are mapping all those uh, pixel values from the input layers. So that is why I call it dense. In this case also, you see, we're taking from all this and mapping it to the next layer. So that's why it's known as dense. And you're also probably wondering what's a ReLU and softmax. I will explain softmax first, what we are doing in softmax. Here you see, uh, if number 7 is a shirt, let's say number 7 is a shirt. So for all these functions, suppose in this is a boot, say this is a pant. So probability of the output being a boot would be probably 0.1 or 0.13, 0.14, like this. And this would be very much high because this is the actual output that we are training the neural network on. So it will be probably close to 1. So this would give a very high value, say 0.99. But so what a softmax does is, it takes a set of values and effectively picks the best one. So for example, if the output of the last layer looks like 0.1, 0.1, 0.05, 9.5, it takes, it saves you from finishing through the, essentially it saves time and memory of the computer, and it does not have to go through all these values. It just trims them down to the highest value. Means all of this would be 0, and the highest value would have 1, right? It saves you from fishing through it looking for biggest value and returns it to 0, 0, 0, 1, 0, 0. See, all these are reduced to 0, and since this was the highest, it's 1. And now you're wondering what's value, right? Again, I'll jump to my paint window to give you a demonstration of what value is. Suppose you are calculating price of a house. This is the size of the house in x-axis, size, this size, and this is cost. Sorry for my handwriting, I'm using a mouse pointer. So yeah, so suppose um, house of cost of house 1 is this, and the size is this. Cost of house 2 is a bigger size, and cost is this. also house 3, house 4, house 5, right? So suppose these are the data points, right? And we need to train a neural network to predict the housing price. So the as you can see, probably the best fit for this function would be this line. However, you see this line is touching, cost is touching 0 if size is less than this point, and below this point this function would actually go further. So cost will go to negative. However, we know that's never the case, right? Cost can't be negative, no matter how small the house is. So in this case, we use a ReLU. We tell it if the value is less than 0, then the output would be 0. So this is a ReLU function, right? So this function is known as a ReLU. Okay. So I explained what's sequential, what's flattened, what's dense, and yeah. So we're out of time already, and so after this, in the next DSC and SCC ML events, we'll be jumping further and looking into more steps like filtering the input before training. We'll also be looking into pooling the input to subsets and using convolutional layers. Um, However, till now we have learned the basics of any neural network, and we can uh, we have actually learned a decent amount, and we can actually develop several machine learning models, and you can actually start uh, coding for some right from this moment. So till now we finish our event here. Now if you have any questions, uh, feel free to ask them. Okay, one after the other. Okay, Hiran Sharkar asks, how does Adam optimizer work? Okay, so Adam is another popular optimizer. Uh, I already have explained Adam in my optimizer part. So, okay, I'll be linking this presentation to the description box, and you can download this presentation, right? And here I've explained all these optimizers and when to use them actually. I've also used Adagrad, RMS prop, and Adam along with stochastic gradient descent. So you can read through this. How do you determine the density of hidden layer? Um, Minindu, I'm not really able to understand how do you determine the density of hidden layers. Uh, we aren't determining something called dense. Dense is actually a type of a layer. Um, this is, wait, okay, I'll share the screen with you. Okay, so this is a dense layer, right? We call it dense layer because since we aren't providing any specific uh, value from this input layers, right? We are providing all these pixel values to the next layer and letting the computer figure out that which values are important and how their parameters are tuned in the function. So we aren't saying that these two these two pixel values would go to this function and such. So we are providing everything in the function and letting the computer figure out. So that is the reason we use a dense there. I hope that resolves. However, if you ask something different, please feel free to rewrite the question. Okay, please explain the relationship between gradient descent and back propagation. Okay, fine. I hope you saw this in my slide. I had written back propagation. Okay. So yeah, back propagation uses gradient descent in a type. Uh, However, for that I need to explain back propagation now. That would be little time consuming. Okay. Could you please post this question to me on Twitter so that I can answer it on Twitter using proper links and demonstration, because back propagation in itself is a really vast concept, and just know that back propagation also uses gradient descent in a way, and I would be happy to help you in my Twitter account as well. What is the best optimizer that works best for most projects? Okay, let me share my screen and see. So, servers. Okay, so for optimizers, I would go with SGD, stochastic gradient descent, and Adam. These two are the mostly used optimizers that you'll find. The next two would be Adagrad and RMS prop. However, SGD is like the grandfather of optimizers, if you'd like to say that. But yeah, SGD is the most commonly used. Adam would be the second choice, and you can go through this slide and you'll learn in which case to use which optimizer, right? What is the best optimizer? Okay. Anything else? Okay, so let's finish this event. It was lovely meeting you all. If you have any queries, as I said, please reach out to me on Twitter at @Rishiraj, and I would be happy to help including this back propagation thing. I have some demo of it prepared as well. I can share it with you in Twitter. So also, I have one demo of log loss. If you are willing to experiment with log loss, you can visit this repository, take a screenshot of it for log loss. This is a very intuitive repository where you can find, and for mean squared error or the loss that we mentioned, this is a line fitted that I used. And okay, so that's it. That's it for this event. Please feel free to check your email for the post-event survey. There you'll get 50% discount in any deeplearning.ai course from Coursera. And stay tuned for further Developer Students Club Netaji Subhash Engineering College events, where we'll clear some of your doubts and jump deeper into machine learning, right? So thank you.